Hi, I'm Joe James, and in this geometry series video, we're going to cover circles. Concentric circles are circles on the same plane that have the same center. As you can see here, two circles, possibly different sizes, that have the same center point. Congruent circles just have the same radius. So the radius of the two circles is equal, the same length. Makes the two circles congruent. This is an important slide because we're going to be talking about tangents, secants, and chords for the rest of this presentation. So a tangent is a line on the same plane as a circle that touches the circle at just one point. So it intersects a circle at a single point. A secant is a line that intersects a curve or a circle at two distinct points. And you can see a secant is intersecting or passing through this circle at two different points. And a chord is basically the same thing as a secant, but it's not a line, it's just a segment. So it has endpoints on the circle. Now, circle tangent theorem says that if a line is a tangent to a circle, we know that it has only one point that intersects the circle, then it is perpendicular to the radius of the circle at the point of tangency. So in other words, a segment coming from the center of the circle to connect a point of tangency is going to be perpendicular to that tangent, a 90-degree angle. So that's the circle tangent theorem. The next circle tangent theorem is if two segments are tangent to a circle, as these two here are, from the same external point, in this case point M, then the segments are congruent. So if point L is a point of tangency and point N is a point of tangency, and these two tangents intersect at point M, then we know that these two lengths are the same length. So ML is congruent to MN. So that's circle tangent number 2. Let's do a practice problem. Given segments DE and DF are tangents on the same circle, find DE. So we know that these two are tangents to this circle, and therefore they must be the same length, they're congruent. So instead of given the measure of these two segments, we're given the length in the form of t. So what we can do is we set these two segments equal to each other. DE is equal to DF, or 2t plus 8 is equal to 4t minus 10, and then we can solve for t. 2t equals 18 by moving all the t components to the same side and all the constants to the other side, and then we can say t equals 9. Now we just plug t equals 9 back into either one of these equations. 2t plus 8 equals 2 times 9 plus 8, and that equals 18 plus 8, which is 26. So each segment is 26. Now let's talk about arcs. A minor arc is an arc whose points are on or in the interior of a central angle. I don't know if we talked about a central angle, but a central angle is an angle whose vertex is at the center of the circle. So A is a central angle because the vertex is at the center of the circle here. So an arc whose points are on or in the interior of a central angle. So in other words, this is a minor arc. A major arc is an arc whose points are on or in the exterior of a central angle. So angle B here, this gray line would be the minor arc, and the red is the major arc, which in this case is bigger than the minor arc. So points inside that angle are the minor arc, points on the outside of that angle are the major arc. Adjacent arcs is when two arcs are on the same circle and they intersect at exactly one point. So here we have RS and ST. We can see that these are adjacent arcs because they intersect at point S, the red arc and the blue arc. So we can add these two, and the sum of the measures of the two adjacent arcs is equal to the measure of the arc formed by the two adjacent arcs. This is no surprise, it's just simple addition, it's common sense. RS plus ST is equal to RST, this whole thing. And by the way, the measure of this arc, we could measure it in distance or length. Also, we can measure it in degrees from the central angle. Congruent arcs. Two arcs are in the same or congruent circles that have the same measure. So if these two circles are congruent, and this is k degrees and this is k degrees, then these two arcs are going to be congruent. Here's another important property about circles and arcs. In a circle or congruent circles, not necessarily the same circle, in my diagram this is the same circle, congruent central angles have congruent chords. So here we see two different angles that are congruent, FCE and ECD. So these are two congruent angles. If the two angles are equal, then these two chords are equal, and the two arcs are equal. Right? Congruent angles means that you have congruent chords and congruent arcs. And that can be either in the same circle or in a congruent circle. In other words, a circle of exactly the same size. The perpendicular bisector theorem states that in a circle, if a radius is perpendicular to a chord, as here, right? We have a chord in green and we can see this radius is perpendicular to it, then that radius bisects the chord and its arc. It splits the chord into two equal segments and it splits the arc into two equal arcs. Sectors. A sector is a part of a circle that is enclosed by two radii and their intercepted arc. So here we can see a central angle and the center point of the circle. Here's a radius, there's another radius in black, and then we also have an arc around it. So it's basically a slice of pizza. A sector is a slice of pizza. Now, to calculate the area of a sector, we calculate first the area of the entire circle, which we know the formula for that is pi r squared, gives us the area of the circle using pi and the radius. And then we multiply that by the fraction of the circle that's covered by the sector. Well, how do we know what fraction of the circle is covered by the sector? Simple. This sector has an angle, a central angle, with a measure of m degrees in this case. And we just put that over 360, which is the measure of an entire circle. It's 360 degrees. M over 360 gives us the fraction of the circle that's covered by this sector. Arc length is the distance along an arc, and it's measured in linear units. An arc also has a measure in degrees, which is the measure of that central angle. So to calculate arc length, we can calculate the circumference of a whole circle. That's just 2 pi r. We know the formula for that. And then we can multiply that by the fraction of the circle that was covered by the arc. So what fraction of the circle is covered by the arc? Well, m over 360. Again, 360 degrees in a circle, m degrees in this arc. So m over 360 times the circumference of the circle. That's arc length. It's a very similar equation to the sector area. So if we look at sector area, pi r squared is the area of this whole circle times m over 360, and arc length is 2 pi r, which is basically the equation for circumference. So let's do a sample problem here, a practice problem. Find the length of arc km and the area sector of jkm. So we're looking for the area of this gray sector and the length of this blue arc. We're given the radius And we're given the measure of this angle, angle J. So let's figure this out. The length, we can just apply our formula here. Let's plug in our numbers. 2 pi r times m degrees over 360 degrees. That's our formula for the length of the arc. So let's plug in what we know. The radius is 10 and m is 45 degrees. So we divide all this out, multiply it out, we get 20 pi times 1/8. And when we reduce that, we get 5 pi over 2. We'll just give our answer in the form of pi. So 5 pi over 2 is the length of this arc. Now the area of the sector is pi r squared times m over 360. We're going to plug in r squared. R is 10, so r squared is 100. We multiply this out, we get 25 pi over 2 is the area. That would be in some kind of square units. The area of the gray sector. Let's talk about inscribed angles. An inscribed angle is an angle formed by two chords of a circle with a common endpoint. A chord, mind you, is a segment that has endpoints on the circle at two different places. So FE is a chord. An inscribed angle is angle EFG is an inscribed angle, and that measures x degrees. So an intercepted arc is an arc whose endpoints lie on the sides of an inscribed angle. So in other words, arc EG here, right? We have inscribed angle EFG, and then we have intercepted arc EG. Now we know that angle F here measures x degrees. So what does the inscribed angle theorem say about the measure of arc EG? It says it is 2 times bigger. 2 times x degrees. So if angle F is x degrees, arc EG measures 2x degrees, which means that a central angle coming from H, the center of this circle, is going to have a measure of 2x degrees, or 2 times bigger than this angle. And this doesn't matter where F is on this circle. F could be up here. If it still intercepts arc EG, then even if F is up here, the same law is going to apply. The central angle is going to be 2x degrees. Let's do a practice problem here. This one looks funky. So given angle RSQ measures 6x plus 12 degrees, so we're given angle S's measure in terms of x, and we're given angle P's measure in terms of x. Find x. Well, gee, that's pretty easy because look, both of those two angles are inscribed angles, and they have the same intercepted arc, RQ, this red arc. So when we look at this, yeah, they're both intercepting the same arc. So we know that these two angles are equal. So now we can just take these two expressions and set them equal to each other, and then solve for x. We'll move the x terms both to one side. We get 4x equals 28. And then we can divide by 4 to get x equals 7. Easy enough. The tangent-secant relationship, we have a theorem. If a tangent and a chord or secant, the only difference is a chord is a segment and a secant is a line, intersect on a circle at the point of tangency, which here is y, right? Chord xy and tangent yz, and y is the point of tangency, then the resulting angle, angle y, measures half its intercepted arc. In other words, half what this arc is. The arc has a measure in degrees, and angle y has a measure in degrees. Also, if we drew a central angle here from y to the center of the circle over to x, That's roughly a 90-degree angle, right? But that would measure twice this angle, which is probably about a 45-degree angle. So that's your sanity check. Here's another theorem about chords and secants. If two chords or secants intersect in the interior of a circle, and here we have two chords, EG and DF, they intersect at point H here in the interior of a circle. Their intersection point is in the interior of the circle. Then the measure of each angle formed is the average of its two intercepted arcs. So this angle, well, first we know that this angle is going to be equal to this angle. These two angles are both going to be the same. But this blue angle here, DHE, is equal to the average of this arc and this arc. So we can add those two arcs together, divide by 2, and that will give us the measure of DHE. Another theorem on chords intersection. We have almost exactly the same drawing here. If two chords intersect in the interior of a circle, then the products of the lengths of the segments are equal. So what does that mean? Well, DH and HF, in other words, light blue times bold dark blue, is equal to GH times HE, or bold red times skinny red. So long segment times short segment is equal to long segment times short segment, okay? So here's a sample problem. Given the circle with intersecting chords with segment lengths as shown, find HE. We're looking for this red distance here. Well, look, we're given these three lengths. How can we find that? This isn't very intuitive. But since we just learned that the product of 4 and 10 is equal to the product of 8 and HE, it's pretty easy to multiply this out. So we just set 4 times 10 equals 8 times HE. We multiply this out, 40 equals 8 times HE. We divide both sides by 8, and we get HE is 5. So this length is 5. If two secant segments are drawn to a circle from an exterior point, in this case point A, then the product of the measures of one secant segment and its external secant segment is equal to the product of the measures of the other secant segment and its external secant segment. So this sounds complicated as heck, man. That is so wordy. Who came up with that? But think of it this way. The whole line up to point C, AC, times the outside portion of it, AB. So AC times AB is equal to this whole line, AE, times the outside portion, AD. So whole times outside equals whole times outside. That makes it a lot more digestible. That's the secant segment theorem. The Secant-Tangent Product theorem is kind of similar. Basically says that the whole times the outside, AD times AC, is equal to AB squared if AB is a tangent and the point of tangency is B. So that's almost exactly the same thing, except that we have one secant and one tangent. And we square that tangent. Ooh, this one looks hairy. Well, there's 3 different cases, okay? You could have either a tangent or a secant, and this same theorem applies in 3 different cases, whether you have a tangent and a secant, 2 tangents, as you have here in the middle one, or 2 secants. And what this theorem says is that if 2 of these intersect outside of a circle, which would be points A, E, and J as the intersection point outside of the circle, then the resulting angle, A, E, and J, measures half the difference of its intercepted arcs. Let's see. Angle X here is the same as A. Point A, angle X. X is equal to half the distance of its half the difference of its intercepted arcs. So angle X is equal to half the difference of its intercepted arcs. So its intercepted arcs are BD and CD. So CD is the long one, we'll put that one first, and BD is the shorter one, we'll put that second. We subtract to get the difference, and we divide that by 2. That gives us the measure of x here. And the same thing here. If we want to find angle y or angle E, y is equal to the difference of, look, this long arc minus this short arc, FH, divided by 2. And same thing here. The intercepted arcs are LM minus this short one, KN. First we subtract, then we divide by 2, and that gives us the measure of angle Z here. So let's do a practice problem just to make sure we understand that. Given the circle with tangents EF and EH and chords GF and GH, find the measure of angle Y. So what is the measure of Y? How are we going to find Y? Well, since angle FGH is an inscribed angle, that's this one, this 50 degrees here, we know that the measure of arc FH, this little gray arc here in the middle, is 2 times the measure of angle G. Measure G is 50 degrees, then the measure of this arc FH is going to be 100 degrees, 2 times 50. So the measure of arc FGH is equal to 360 minus 100, right? The whole circle measures 360 degrees, and we know what FH is, it's 100. So we just subtract 100 and we get 260 for this big arc, FGH. Now we know this long arc, and we know the short arc for Y. So what do? We just subtract and divide by 2. Right? We 260 minus 100, 260 for the big arc, 100 for the little arc, and we divide by 2 and we get 80. So the measure of Y is 80 degrees. So let's try graphing circles. This is actually not that hard. It's kind of fun, really. The equation for a circle is x minus h, quantity squared, plus y minus k, quantity squared, equals r squared, where r is the radius. HK is the center of the circle. So h and k are the center of the circle. Those are our xy values for the center of the circle. So if we have a center of -2, 1 and a radius of 3, what does that look like as a circle on a graph? Well, it looks like this. Let's start at the origin. We'll count left 2 and up 1, and that gives us the center of the circle. We can see a radius of 3, so we could go outwards 3 in any direction, and we could draw a circle, and this is what the circle is going to look like. So to write the equation of that, x plus 2, wait, why is it plus 2? Because we have a -2 here, and this negative is part of the equation. So those two negatives cancel each other out, and we get x plus 2. And then here we have a y minus whatever k is. Well, k is a positive 1. So y minus 1, quantity squared, equals 9. That's the equation. An inscribed quadrilateral theorem says that if a quadrilateral is inscribed in a circle, as we have here, TUVW, then its opposite angles are supplementary. So angles U and W add up to 180, and T and V add up to 180. Opposite angles are supplementary. Now here's a practice problem on circles. This is kind of a neat problem. We have to find the area in blue. All we're given is one side of this square, 8. That's all we're given. We have to find out the area in blue. Well, let's think about this. We could find the area of the circle and then subtract the white area, which is the area of the square. We just subtract that out of it, and that will give us, what's left will be the blue area. So how do we find the area of the circle? We need a radius. We need a radius. So what we need is, well, this diameter is 2 times the radius. So we need to figure out what this is. How can we find that? Well, look, we know 8. We can know this side because these two sides of the square are the same. Now, all of a sudden, you look at this red here, and what do we have? We have a 45, 45, 90 triangle. With the 45, 45, 90 triangle, what do we know? That the proportion of the sides are 1 to 1 to root 2. Or for our little triangle here, the sides are going to be 8 to 8 to 8 root 2. Now we know the diameter of the circle. We can divide that by 2 to get the radius of the circle. So the radius of the circle is 4 root 2. Wow, now we're well on our way. We know the radius of the circle, so we can calculate the area of the circle using that radius, and then we just subtract out the area of the square. So the area of the blue space is equal to the area of the circle minus the area of the square. The area of the circle is pi r squared, and the area of the square is just 8 squared. So the area of our circle is pi times 4 root 2 quantity squared, which multiplies out to 32 pi minus 64, and that's as far as we can reduce that. 32 pi minus 64 is our final answer in terms of pi. That concludes my video on circles. I hope you found this video helpful. If so, please click the thumbs up and subscribe to my channel. I'm Joe James. Thanks for watching.